Hi, I'm Prof L and welcome to Chemistry Matters. And today we are going to continue our delve into chemical kinetics, and we are going to do a few practical examples now of the sorts of questions that you might reasonably expect to come up in a test or an exam. Last time we talked about how we define the rate of a reaction, and if you recall, what we defined the rate of this reaction as being AA going to BB. We said that the rate of that reaction is negative 1 upon little a dA by dt is equal to 1 upon B d big B by dt. Okay, what do we actually do when we are doing chemical kinetics? I mean, what's the whole point of the thing? And what we really want to know, the piece of information or pieces of information that we want to know, okay, yes, we want to know how fast the reaction goes. Yes, that's important, but more important still is how does the rate of a reaction depend on the concentrations of the reactants? Okay, and indeed in some cases the products, but we're not going to go there because that's getting too deep. Okay, so what we do when we do chemical kinetics is we try and find out that particular piece of information. Does the rate depend on the concentration, the starting concentration of A in this case, okay? Or does it not, okay? And if it does, how does it depend on that concentration? In what way does it depend on the concentration? Is it a linear dependence? Is it a squared dependence, a cubic dependence, etc., etc.? That's really, really important. And essentially, that's why we do chemical kinetics. That's what we're trying to find out, is how the rate depends on the concentrations of the reactants. Okay, so what we are then going to do is we are now going to write a thing called a rate law that takes that into account. Okay, we're saying that the rate of the reaction, yep, it equals this here, minus 1 upon A dA by dt equals 1 upon B dB by dt, but it also is equal to some constant K, little k, that we are going to call the rate constant. And it is then going to be equal to the concentration of A to a particular power that we're going to call X in this case, okay? So the rate of the reaction is equal to some rate constant K multiplied by the concentration of A raised to some power X. Okay, and this has a special name. X is called the order of the reaction, in this case with respect to the concentration of A. Okay, so you got to say that this bit here looks a hang of a sight simpler than this bit here. And yes, it is, okay? So let's go more general still. Let's say, right, we've got a chemical reaction of A and B, okay? So we've got A moles of A plus B moles of B, and I can't draw a B to save myself, plus B moles of B, giving C moles of C plus D moles of D. And what we're going to say is that the rate of that reaction is equal to some constant K multiplied by concentration of A to the power of X multiplied by the concentration of B to the power of Y. Okay, and this is a thing that we call the rate law. And just reminding you, K, little k as opposed to big K is equilibrium constant, little k is rate constant. Okay. So, obviously X and Y are all important here. We don't know what they are. We've said that we could measure the rate. We showed you how to do that last time. We can use the method of initial rate so that we can measure We can measure the concentration of A, we can measure the concentration of B. We don't know what X and Y are. And we also don't know what K is. So we want to determine those. Okay, and you might think, okay, one equation, three unknowns. How do you do that? You do lots of experiments. Okay, now the beauty of kinetics, and the thing that makes it a lot simpler than it actually looks, is the fact that X and Y, these orders, are very, very often, almost exclusively, X and Y is equal to 0, 1, or 2. That's basically it, okay? Small positive integers. And that makes life a lot easier. So X and Y can't be anything that they want to be. They are pretty much always 0, 1, and 2. And the reason for that is these orders of reaction tell us something about what's happening on the molecular scale, okay? So the molecular scale, we've got, remember, our molecule of A and our molecule of B. And what has to happen in order to get reaction occurring generally? Remember, A and B have to collide. Okay, you've got one of this and you've got one of this, and that's what those orders reflect. Essentially, the number of atoms, molecules, ions, or whatever that have got to collide in order for the reaction to happen. So this is a very, very simple way of figuring out what's going on the molecular scale. That's kind of cool. Okay, so how do we determine X and Y? That's the question. Okay. Now, the answer to that is that we, as I said, we do lots of experiments where we change the concentrations of one of these and keep the other one the same and see how the rate of the reaction depends on those concentrations. Okay, so first up, before we get into this in a big way, let's just very, very quickly introduce some terminology. So if X is equal to 0, we call that, surprise, surprise, a zero order process. If X is equal to 1, then we call that first order, surprise, surprise. And if X is equal to 2, then we call that a second order, okay? And what we generally do is talk about the total reaction itself. So we sum X and Y usually. Okay, so the overall order of the reaction is given by the sum of the individual orders. Okay, so the individual orders are with respect to the reactants, the concentrations of the reactants. The overall order of a reaction is dependent on the sum of the individual, all of the individual orders. So we talk about generally a zero order reaction, a first order reaction, or a second order reaction. Okay, so how do we find out those individual orders and the overall orders of the reaction and also the rate constant? Well, this is classic exam question fodder, basically. The answer to that question, how do we determine those individual orders? We get given data, which come from a whole heap of experiments that we do. We then analyze those data, and from an analysis of those data, we can generally figure out the individual orders of the reaction and the overall order of the reaction. Okay, so here is the first example that we are going to be looking at, okay? SO2Cl2, sulfuryl chloride, nasty stuff. And it is reacting to give SO2, sulfur dioxide, and Cl2 chlorine gas. Okay, so this would be a classic exam question, and the question would go something like, determine the order of the reaction with respect to the concentration of SO2Cl2, given the following data. Okay, so let's check these data and see what they are telling us. Okay. So what we've got is concentration data, and we have got rate data, specifically initial rate data, okay? So the initial rate says that, remember, that the initial rate is basically linear. So the plot of concentration versus time is essentially linear right at the start, and we can get those initial rates quite happily. Okay. So initial concentration of SO2Cl2, we're given those, and we're seeing that they change. Okay, 0.1, 0.2, 0.3. And the initial rate of formation of this, of one of the products, these rates are given here, and you can see that they all change as well. So that's what we're doing. We're taking our reaction. We start off with a particular concentration of sulfuryl chloride. We measure the rate under those conditions. We then, in this case, double the initial concentration, and we see how the initial rate changes, if indeed it does change. And again, we now triple the initial concentration of sulfuryl chloride, and again, you're looking at how the rate changes, okay? So how do we then figure out what is going on, what the order of the reaction is with respect to sulfuryl chloride? Well, let's look at the data. Okay, so we have our first piece of data here, 0.1 initial concentration, 0.1 mole per litre, the initial rate of formation of SO2. Now, the one thing that we haven't talked about yet is units, okay? Now remember, so what we can say about this particular reaction is that the rate of the reaction is equal to negative concentration of DSO2Cl2 with time, okay? So remember, slope of the graph of the concentration of SO2Cl2 with time. What's the units of concentration? The unit of concentration is the mole per litre. What's the unit of time? The unit of time is the second. It's on the bottom line. So therefore, the unit of the rate of any reaction is always the same. It's the mole per litre per second. Okay, which kind of makes sense when you think about it. How is our concentration changing with time? Okay, in other words, how many moles per litre are we churning through in each period of time? That's our rate of reaction. So that's the units of the rate of the reaction. Okay, so back to our data now. Our first piece of data is there for comparison to the other pieces of data. Let's look at the second one here. Now, what have we done? We've doubled the initial concentration of SO2Cl2. And the initial rate of formation of SO2 has also doubled. Okay, now if you compare 1 and 3 here, you can see between 1 and 3 we've tripled the initial concentration of SO2Cl2. What's happened to that initial rate of formation? It's gone from 2.2 by 10 to the minus 6 to 6.6 by 10 to the minus 6. It's tripled as well. So there looks to be some sort of linear relationship here. Okay, from what I told you before, the rate law for this reaction is going to look something like the rate is equal to K times the concentration of SO2Cl2 to the power of some unknown order, X. And remember, we're saying X is 0, or it's 1, or it's 2. So let's have a look at those three possibilities and see how they compare or not with the data that we've got here. Let's assume that X equals 0. So if X is equal to 0, then the rate of the reaction is equal to K itself. Because remember, anything to the power of 0 is equal to 1. Okay? So if we're talking about a 0 order reaction here, the rate law for that reaction is that the rate is constant. It doesn't change. It doesn't depend on the initial concentration of sulfuryl chloride here. Okay? If X was equal to 1, in other words, if it was a first order reaction, then the rate of that reaction would be K multiplied by the concentration of SO2Cl2 to the power of 1. And remember, anything to the power of 1 is just itself. Okay? If X was equal to 2, then the rate of the reaction would be K times concentration of SO2Cl2 squared. In other words, we'd have a squared relationship. So you can see from these three equations here how we are going to figure out what the order of the reaction is, because each of them is very different. If it's a zero order reaction, as we change the concentration of sulfuryl chloride, the rate shouldn't change. Okay? The rate shouldn't change. We can see that the rate does change as we change the initial concentration. So that is straight away saying this can't be a zero order reaction. Okay, let's skip x equals 1 for soon to be obvious reasons. Let's go to x equals 2. So that's saying that the rate is equal to some constant, which we don't have to worry about yet, multiplied by the concentration of the SO2Cl2 squared. Okay, so in other words, the rate is related to the concentration in a squared fashion. As we, for example, double the concentration, the rate should go up by a factor of 2 squared, which would be 4. If we triple the initial concentration, then the initial rate should go up by a factor of 3 squared, which is equal to 9. Okay, there's a squared relationship between them. Do they do that? Is that what these data are saying? Well, as we double the initial concentration, the rate of formation, the rate of reaction goes up by a factor of not 4, but 2. Okay? As we triple the initial concentration, the rate goes up by a factor of not 9, but 3. So we can say, no, it's not a squared relationship. Okay? So that just leaves first order. And first order is a linear relationship between the rate of the reaction and the concentration of sulfuryl chloride. As the rate doubles, as the concentration doubles, the rate should double. As the concentration triples, the rate should triple, etc., etc. Linear relationship. Have we got that? Yes, we have. Okay? So, as this initial concentration doubles, the rate doubles. As the initial concentration triples, the rate triples. This is a first order reaction. And the rate law for this first order reaction is rate is equal to K multiplied by the concentration of sulfuryl chloride to the power of 1. First order reaction. Okay, we've nearly answered the question. And the one thing that we need to do now is determine what the rate constant is. Okay, the value of K. So let's go ahead and do that. And the way that we do that is, first of all, we need our rate law that we've just determined. So the rate of the reaction is equal to K multiplied by concentration of SO2Cl2 to the power of 1. That's it. Okay? So let's rearrange that equation and say, right, so K is then going to be, we're going to divide both sides by SO2Cl2, okay? So therefore K is going to be the rate of the reaction divided by the concentration of SO2Cl2. And that is going to give us our value of our rate constant. So this is a straightforward plugging in the data type of question here, okay? Now, the one confusing thing in this, or can be confusing, is the fact that you're given 3 sets of data. Okay? You're given initial concentrations of 0.1, 0.2, 0.3, and their associated rates. Okay? So, which piece of data do you use? Do you use the first, the second, or the third? If you've done it right, all of them are going to give you the same answer, so it doesn't matter. Okay? So let's do it just for the first one. Plug in the numbers, so K is equal to the rate over concentration of SO2Cl2, so we're going to have 2.2 times 10 to the minus 6. And again, remember, put in your units all the time, because that's important, because we're going to see that K has different units depending on the order of the reaction. So that's going to be mole per litre per second divided by, in this case, 0.100 mole per litre. You can see here that the moles per litre are going to cancel out, and we are going to get left with 2.2 times 10 to the minus 5 seconds to the minus 1. And let's just write that up here in case I'm going off the bottom. So K is equal to 2.2 times 10 to the minus 5 seconds to the minus 1 for this particular reaction, okay? And that's the value of your rate constant, okay? So, I said that the units of rate are always the same, and this is where people get confused. The units of rate are always moles per litre per second. The units of the rate constant depend on the order of the reaction. If the reaction is a zero order reaction, the rate of reaction is equal to just K, so therefore the units of K are going to be the same as the units of rate are going to be mole per litre per second. If the rate of the reaction is equal to K times, in this case SO2Cl2 to the power of 1, then the units of K are going to be seconds to the minus 1, and if it was a second order reaction where we had SO2Cl2 squared, the units look very unusual, mole to the minus 1 litre seconds to the minus 1. Probably something you haven't seen before there. Okay, so that's how to do those types of problems. You're just looking at the data, looking to see how the rates of reaction depend on those initial concentrations. Let's quickly do one more, just to make sure you're getting the hang of this. This one a little bit more complicated because now we've got two reactants, and so therefore we need to vary one of those reactants while keeping the concentration of the other one the same. So we will quickly do another one here, and just to make sure that you've got the hang of all of this. So this one's a little bit more difficult because you have got two reactants in this case. So we've got 2NO plus H2 giving into plus 2H2O. And let's stick a 2 in there as well. Okay, so we've got our balanced chemical equation here. And what we've got now are data relating to both of the reactants, okay? So we've got NO and we've got H2. And we're going to vary the concentrations of these, but we're only going to vary the concentration of one of them at a time. We're going to keep the other one constant, okay? Because obviously we need to know how the rate varies as we change the concentration of only one of them. If we change the concentration of both at the same time, yes, you can still analyze it, but it gets a lot more difficult. Okay, so let's go through the same way that we did with our previous example. So you can see from these first two pieces of data here, what is happening is that we're keeping the NO concentration constant and we are doubling the H2 concentration. And when we do that, the rate of the reaction goes up by a factor of 2. Okay, so what is that telling you? Well, remember we're going to have a rate law that looks something like rate of reaction is going to be equal to K times the NO concentration to the power of X times the H2 concentration to the power of Y. Okay? So, if we keep the NO concentration constant, which we've done in between 1 and 2, and we double the H2 concentration, we see that the initial rate doubles, and so that tells us straight away this is a linear relationship. You're doubling the concentration, you double the rate. That's a first order process, and so we can straight away say that this is going to be first order with respect to H2. Okay? You then look at, if you look at 2 and 3, so experiments 2 and 3, you can see they both change. The concentrations have both changed, so we can't really use those. But if you look at the experiment 1 and experiment 3, you can see that the H2 concentration in this case is being held constant, and the NO concentration is doubling. And if you compare the rates of the reaction under those conditions, you can see that the rate goes up by a factor of 4. Okay? So we've doubled the NO concentration. We have increase the rate of the reaction by a factor of 4. That's a squared relationship. And so therefore we can say that this is going to be our rate law now, that the rate of the reaction is equal to K times NO squared concentration times H2 concentration to the power of 1. And anything, remember, to the power of 1 is just itself. So from these particular data, the rate law for this reaction, rate is equal to K times NO squared times H2 concentration. And there you have it. And again, we haven't quite finished, because again, we are going to find out what is the rate constant for this reaction. And so remember, the rate constant is just going to be obtained by rearranging this equation. It's going to be the rate over the NO squared concentration, or NO concentration squared, multiplied by concentration of H2. And again, you can choose any of these three pieces of data to figure out what your rate constant is going to be. We could choose the second one here just for something different. So that's going to be 2.46 times 10 to the negative 3 mole per litre per second. And that is going to be divided by, in that case, the NO concentration is 0.1 squared, and the H2 concentration is 0.2. And the answer that you get for that is then going to be 1.2, and we're getting very unusual units here. Mole to the minus 2 litres squared seconds to the minus 1. Very, very unusual, okay? But it all works out. Okay, so now that and these last two videos have been a very, very gentle introduction to this whole science of chemical kinetics. There's a heck of a lot more to learn about chemical kinetics. We didn't really get into the whole maths side of things, etc., because that's sort of secondary, really. The important thing is figuring out the orders of the reactions and interpreting those particular data. So if you can do that sort of stuff, then that should hopefully see you through the better part of first year chemistry, wherever in the world you are anyway, okay? So with that in mind, we will finish kinetics now, and we'll see you in the next video. Okay, see you later.